Okay, so now getting into the actual examples of using Rolle's theorem and how things are going to be asked. It says to find the two x-intercepts of the function f and show that the derivative of the function is equal to 0 at some point between the x-intercepts. All right, so the first problem function that we're going to look at is the x squared minus 3x plus 2. So first of all, we've got to find our x-intercepts. So if you remember to find x-intercepts, then you can let y equal 0. Of course, f of x is the same thing as y. So that means what we're going to be doing is setting this quadratic equal to 0. So I did that, and then at the same time I went ahead and factored it, because that's what you'll need to do if you're wanting to find the values that make it equal to 0. So of course you solve your first factor, you're going to get positive 2, and that's just an equal sign there. Those random dots, remember, just show up when I print them off. Then if you solve x minus 1, then you're going to get x equal positive 1. So that would be the location of the two x-intercepts. So that would, of course, just be the point 2, 0 and the point 1, 0. So then it says to show that the the derivative, or find where the derivative is equal to 0 at some point between the intercept. So what this means is you're looking at a closed interval, your closed interval, that it kept referring to on those definitions that we were looking at before, will be from 1 to 2, because you're finding a value in between 1 and 2 is what you're looking for. Okay, now just a couple of statements that I had gone ahead and written down here, just to kind of help make a few things make sense. It says the interval is the closed interval from A to B, and we know that it's continuous because it's a polynomial function. Actually, I swear I meant to write the 1 to 2. So your interval is the closed interval from 1 to 2. Okay. Now, you remember it kept, in the definition of Rolle's theorem, it kept saying that it needed to be continuous on the closed interval. Of course, you could look at it on your calculator if you choose to do so. But the fact that it's just a polynomial, you know that polynomial functions are always going to be continuous. Okay, the other thing is, remember that f of a is supposed to be equal to f of b. So if you were to substitute 1 back into your function and work it out, and then substitute 2 back into your function and work it out, then you would actually, end up with 0 equals 0. Of course, they're both coming out to be equal to 0 because they're x-intercepts, but that's what has to happen. Those functions' values have to be the same. And as it states, it says, because of these two things, we know that Rolle's theorem applies. Now, I talked about it being continuous on the closed interval. I didn't write this down, but it is differentiable, and it just goes back to the fact that you know what polynomial functions look like. Remember, they're just, smooth, rounded. The curves in them, what I call hills and valleys, are just smooth and rounded. So you don't have any sharp turns. You don't have any places that they're not continuous. So it's also going to be differentiable. Okay, so we've gotten our x-intercepts. This is just, explanation that you've got to think through each time just to make sure that Rolle's theorem applies. Now, it wanted you to find, remember it said to find where your derivative is equal to 0. So your next step is to take your derivative. Okay, so that's just going to be power rule. So taking your derivative of your function, you'll have 2x minus 3. Now we want to know where is our derivative equal to 0. So therefore I set 2x minus 3 equal to 0. I get x equal 3/2. Now the thing is, most of these problems are going to be set up for you so it works out the way it should, but this is supposed to fall within your interval. And if you remember, our x-intercepts are given our intervals, and that's from 1 to 2. And of course, 3/2 is between 1 and 2. So this would be our x value in which we would have a horizontal tangent line, because remember our derivative is going to be equal to 0. Okay, next. Oh, I know one thing I was going to say about this last problem. I mean, you can always look at this on your calculator if you wanted to. Of course, like you could type it in your y equals. And just make sure what you found makes sense by what you're seeing. Okay. Now, if you were to zoom into this area here a little bit more, of course, you can see that it dips down here below. So right here at the bottom is where you should, or where you will, have a horizontal tangent line, okay? And of course, that is that value of 3/2, because right here is your x equal 1. You can barely see that tick mark, and right here is your tick mark for x equal 2. So see, right there would be your 3/2. So like I said, you can always take a look at it on your calculator to verify. All right, determine whether Rolle's theorem can be applied. If Rolle's theorem can be applied, find all values of c such that the derivative is equal to 0. Okay, so as far as Rolle's theorem applying, this is a polynomial. Okay, so again, same thing I told you a while ago. You've got small, smooth, rounded curves. It's always going to be continuous, so you don't have to worry about it being continuous. It's going to be differentiable, okay? Now, first thing that you're going to need to do is make sure that f of a is equal to f of b, okay? Because if f of a is not equal to f of b, then it's not going to apply. Of course, a is going to be the 1, b is going to be the 4. So the question is, f of 1, is that equal to f of 4? Okay, so you just substitute 1 into your function, and if you do, then that's going to give you 0. And then you're going to substitute 4 into your function, and that's going to give you 0. Okay, so like it passes that test. We know it's continuous, we know it's differentiable. F of a is equal to f of b. All right, so we're good to go on all that, which means Rolle's theorem will apply. So that means we need to find where is our derivative equal to 0. So you need to find your derivative, which is just going to be power rule. And then you're going to set your derivative equal to 0. So therefore, you're going to get a value of 5/2. Okay, now, in order for this to be the value that you're looking for, then this would have to fall within this interval. And of course, this is the same thing as 2.5, which would be in your interval from 1 to 4. So this is similar to the one I did just a few minutes ago, except this one gave you the closed interval a while ago. You had to find the x-intercepts because it wanted you to use the x-intercepts as the closed interval. Okay, next. Okay, so first of all, again, figuring out, does Rolle's theorem apply? So let's figure out about f of a equal f of b. So this is a, this is b. So f of -1, is that equal to f of 1? Okay, so if you were to substitute in -1 and work it out, you're going to get 0. If you substitute +1 in here, then you're also going to get 0. So f of a is equal to f of b. It's not always going to be 0 equals 0. It's just several of these examples are set up where that happens, but it could be 5 equals 5, just as long as it's equal. All right, now going through the other criteria, first of all, your Rolle's theorem states that your function has to be continuous on the closed interval, okay? Now, this being a rational function, having a fraction, What you always have to worry about is what values cause your denominator to equal 0, because there will be some kind of discontinuity at that point. So what's going to cause my denominator to equal 0 is going to be 0. So x equals 0 causes, and this is just kind of an explanation for you to have in your notes, causes the denominator to equal 0, therefore not continuous at x equals 0. Now, if this is not in your interval, there's nothing to worry about. Like, it could be, or it could have a discontinuity at x equals 5, and you would still be able to move forward with Rolle's theorem because 5 is not in this interval. But because 0 falls in your interval from -1 to 0, Rolle's theorem is not going to work here. It's not going to apply. So Rolle's theorem does not apply. We'll just say because function kind of saying some of the same thing I've already said, because function is not continuous at x equals 0, and this is in the closed interval. Okay, so writing a lot of explanation there, but that way when you're looking back at your notes, you'll remember why in the world did we say Rolle's theorem doesn't exist. Okay, one more example here. Okay, so first of all, remember, go check f of a equal to f of b. Again, this is a, this is b. So f of 0, is that equal to f of 2 pi? Okay, so that means I'm going to have cosine of 0, and I'm going to have cosine at 2 pi. Now, you can either think about what your graph looks like, use your table, you know, whatever you're going to use there to help you out, but these are going to be equal to each other because it's going to end up being 1 equals 1. Okay, if you remember your sine graph, just a rough sketch of that standard cycle that, you know, we used a lot. Remember, your cosine graph does this. So see, this is 0, it's up at 1. This is the 2 pi, and it's also up at 1. So it does pass that test, okay? Now, it is continuous. Again, you know enough about your cosine graph. This is just hill after hill, or hill after valley, hill after valley. And there aren't any interruptions in that graph, so it is going to be continuous on your interval. It's also going to be differentiable because, again, it's continuous. There's not any sharp turns. It's not unbounded, so you're fine as far as the differentiability is concerned. So that means we're going to find out where is our derivative equal to 0. So you need to find your derivative. Of course, derivative of cosine is going to be negative sine. And then we're going to set this equal to 0. Of course, divide by -1, so that's still 0. So where is cosine equal to 0 within this interval? And again, if you want to think about what your sine graph looks like, you can use that to help you out. Remember, your sine graph does this. So from 0 to 2 pi, it's at 0 at those three locations. Now, the only one that they're actually going to have as the answer is going to be the midpoint here, which is at pi, because this is 2 pi. Because if you remember the definition of Rolle's theorem, let me flip back here to it real quick. It just states, remember, that there must be at least one x value that's going to be between A and B. Okay, so if you're going to be, between A and B, that means that you're not going to actually count the A and the B as these X values. That's not what you're looking for. You're looking for the part that's interior. So since this is the end points of your interval, that's why you wouldn't see those listed. You would just see the X equals 0. Okay?